For years, autonomous artificial intelligence relied heavily on reinforcement learning. Developers trained systems by defining strict reward and penalty functions. If a cleaning robot picked up dirt, it gained points. If it crashed into a wall, it lost them. The constraint of this approach is scalability. Reward functions are difficult to generalize. You can easily score a robot vacuuming a floor, but you cannot easily compute a mathematical score for a system trying to manage a complex, unpredictable enterprise workflow. Large language models solved the generalization problem. They can process and reason through almost any domain of human knowledge. Yet they possess a severe structural limitation. They are entirely trapped inside a text box. A base language model operates much like a parrot. It is highly fluent and capable of perfectly imitating human speech patterns, but it has no capacity to execute the physical or digital actions it is describing. The core engineering challenge of modern AI is bridging this exact gap. Developers are working to extract the reasoning capabilities of large language models and place them inside systems that can actually sense an environment, process information autonomously, and take independent action. The first step in creating an active agent is supervised fine-tuning. If a base model is an imitating parrot, this stage is like training that parrot to follow direct commands by showing it thousands of examples. Next, developers apply reinforcement learning with human feedback. This process acts like training a lion in a circus, using targeted rewards and penalties to guide and shape the model's behavior. Combining these techniques produces an instruct model, a system optimized specifically to follow human intent. It blends the raw intelligence of the base model with strict behavioral compliance, resulting in a hybrid engine ready to be put to work. But a mechanical question remains. How exactly does a text processing model accomplish a real-world digital task? This diagram shows the translation process that solves this problem. The model parses a user's raw text intent and converts it directly into structured JSON data or Python code. This code then enters a continuous sense-think loop. Within this loop, the agent uses structured prompting frameworks like Chain of Thought or React, forcing the model to reason through complex problems one step at a time, instead of guessing the final answer immediately. As the reasoning progresses, the generated code is used to trigger external pluggable tools. The agent might execute a web search or query a secure database, pulling live data back into its reasoning process. The system repeats this entire cycle, thinking, coding, searching, and evaluating, completely autonomously until it confirms that the original user request is fully resolved. Combining fine-tuned human intent with the ability to write and execute live code forms the exact mechanical engine of autonomous AI agency. To control this engine, developers build a harness. This harness provides the constraints and explicit tools required to keep the model strictly focused on deliberate, goal-directed action. Engineers construct these harnesses using specialized orchestration frameworks. Tools like LangChain, Llama Index, and small agents provide the standardized code needed to connect the language model to external software and manage its step-by-step workflow. As these frameworks mature, developers are scaling up from single-agent systems to multi-agent architectures. Instead of relying on one massive model to do everything, they deploy multiple specialized models that collaborate to solve distinct parts of a larger problem. This diagram shows the two primary ways these multi-agent systems are structured. On the left, a hierarchical supervisor node dictates tasks to specialized subagents. On the right, a leaderless swarm allows equally connected nodes to collaborate and communicate in a decentralized web. Structuring AI in these specialized networks enables the technology to move past answering single isolated prompts, giving it the capacity to manage complex, multi-step operations across an entire enterprise. This rapid execution is pushing the technology into near real-time applications. Frameworks like LiveKit chain together voice activity detection, speech-to-text, reasoning, and text-to-speech in milliseconds, creating fluid, unbroken verbal conversations between humans and agents. Because an agent might pull from dozens of independent tools and databases, each with their own update cycles, the entire system is fragile. To prevent the software from breaking post-deployment, the industry is quickly adopting rigid communication protocols, like Anthropic's MCP and Google's A2A, to govern how agents and resources interact. Empowering an AI to take independent action heavily escalates security risks. Traditional software vulnerabilities are now compounded by unique language model threats outlined in the OWASP Top 10, including prompt injection attacks and the accidental leakage of personally identifiable information. Securing and evaluating these systems is difficult because agentic AI is inherently non-deterministic. Traditional software testing relies on predictable outputs, which fails when applied to a model that can invent multiple valid pathways to achieve a goal. This diagram illustrates how developers test these fluid systems, using frameworks that evaluate multi-layered operations, like retrieval-augmented generation. They must measure retrieval quality, generation quality, and overall task success against a highly curated reference baseline known as a golden dataset. The convergence of memory, tool use, and multi-layered evaluation marks a shift in how software functions. AI now acts as a digital workforce capable of executing complex commands autonomously.